We did the Chapter 7 tests. They're graded. The other class hasn't taken it yet. I'm going to sit on them. And so I've got the other classes and like the makeup's figured out and that kind of stuff. So they're done. You can look at your scores. If you want to come in and look at something in particular or talk to me about something, I'd be happy to do that. I'll get them back to you once most of them have been done or whatever, the makeup schedule and all that jazz. But in the meantime, I'm gonna sit on them. But if you need to look at it, I need to see what happened, that's fine. You can talk to me and we can go through it or whatever. Reminder, at some point this week, we should be trying to make a IA submission. Some of you guys have already started that. I've got a couple of emails in on some people. Some people have suggested topics and been approved already, just a couple. So there's lots of stuff left. Some people have suggested things. I'm like, it's not really going to work, and giving them a reason why. Most common reason is usually that the two things are already known to be related. Like somebody wanted to do, time spent doing this versus time spent doing that, and it's like, well, it doesn't work because there's only 24 hours in a day, so automatically, unless you can do the two things at the same time, you spend more time doing this one thing, you have to spend less, you have less opportunity to spend time doing the other thing, Tommy?
And I'm just gonna send you it.
Yeah, sure.
Let me know.
Yeah, absolutely. Again, you can do it that way. Even if it's a situation like, I think for that person had two things with time, I sent them back to explain to them why we can't do that, but it's like, look, the two variables you want to look at are fine. Can we do not both of the measure with time? And that's fine. Brooks?
So, obviously we're only allowed to be something based off of descriptive, statistics and stuff like that.
That's the plan, yeah.
Okay, cool. Thank you.
So you could use a publicly available data set, but you need some raw data somewhere. So could you use census data and do your own thing and not have to survey anyone? Absolutely. Have people use professional sport league data or NCAA data? Absolutely. There's lots of publicly available. I think somebody used traffic data or movie database data. You can be creative. It doesn't have to be something that's surveyable amongst your peers. So if you have some publicly available data that you can use to sample from, if you can find it, that would be the only concern I would raise. I have it right here. This is where I go, and this is I'll look at it and be like, okay, that looks great. So, the answer to that is depends on if you have the data or not. You need the person's raw data. Most of the published studies don't have that with it. Right, or if it's just based on, census data or something else that's publicly available, you can certainly do that. Everybody cool with that? So again, if you haven't gotten started on that or forgot that that's something I need to do, make a note to yourself and try to get that thought about this week and some ideas sent in at least, so I can start cycling through this in case you get somebody beats you to your idea, and you can submit more than one in case you have backups, or just that your ideas I shoot down because it seems infeasible, or you're measuring something that there's already existing relationship. Kevin, you emailed me about a consumer price and rate of inflation and something. I'm like, well, those two things are already linked. As inflation goes up, consumer prices automatically go up, kind of thing. So it's I really think that's gonna show you a whole lot. But it gives you a chance to you want to have some time in case they come back and I'm yeah, you probably don't want to do that because. And I give you a decent reason. So just kind of put that in the back of your minds. If you've kind of forgotten about that, it's easy to get sidetracked. I know we're very busy. Today we're going to start talking about or continue talking about statistical analysis. Specifically, we're going to be talking about like hypothesis testing here for this chapter. So like, this tends to be from a math standpoint, one of the harder topics we handle in semester one. Not that the calculation is tremendously difficult, but like, you're gonna have some choices of like, oh, what kind of tests should I be doing here? So you have to really understand what they're for, and you're gonna have to understand like what the result means and how to interpret that. So conceptually, this is probably like one of the one or two most difficult topics we do in the course is what we're doing in this chapter right here. So if you, as much of an A game for math as you have, you know, like lock in and bring it. This is only a 2-section chapter, just as a heads up. Oh no, don't worry, we're gonna settle in and like go deep into these 2 sections. Section 2 will be split over 2 days, probably. I have activities and worksheets and stuff that we'll practice these techniques on to get you some more forced practice. But just letting you know that's kind of in the works. Yes, sir.
I forgot like that one another class. Can you put that in
Yeah.
Appreciate that.
All right. Here we go. So again, we're going to be looking at hypothesis testing, and there's kind of 2 different ways you might do that. So we have an example. Imagine trying to figure out how long, on average, it takes to install a new graphics card in a system. This is like installing a part in a computer, right? Everybody's okay with the terminology? The old graphic card installation took, on average, that's the symbol for mean, right? X bar or mu. That's that little thing that looks kind of like a lowercase letter u. It's actually the lowercase Greek letter mu. For the letter M, it's supposed to kind of look like a cursive letter M. And it had a standard deviation of 0.2 minutes. So that's for the old card. We want to test if the new card meaningfully takes longer or not. So the new card, it's said, is the new mean time is 2.2 minutes for install. And when testing these installation times, you want to know if there's a reasonable chance of getting a sample with an average of 2.2 minutes. So what we're talking about here is called sampling error. That means even if the sample were picked correctly, like we did a random sample, we picked random cards and had them installed and timed how long it took, there's still a possibility that we picked like a bad sample, right? If it's random, there's still a chance that we picked like, if we picked 10 graphic card installs, we picked the 10 slowest times or the 10 fastest times or something. Like there's still a chance that could happen, right? That we could get some really unrepresentative sample, even if we did it randomly. What we're going to be doing is we're going to be testing if the probability that the chances of us picking such a terrible sample that we got lies above or below a certain threshold is kind of the idea here. We'll go deeper into this. So we go back and we look over our old installation targets to determine the likelihood of getting a mean that's more than 2.2, given that the old installation was a 2-minute installation with a 0.2 standard deviation. So we're looking to see what's the probability, the likelihood, the chances that we get a mean greater than 2.2. So we're still looking at that same situation, right? So let's say we built out this graph that represents the distribution showing a mean time of 2 and a standard deviation of 0.2. So here's my new mean of 2.2. Yes. Okay. That's the right thing. So we have like mean of 2, 2.2, and if we look at the area under that distribution, the area under that distribution is going to represent the probability that we select a sample whose mean was 2.2 or greater. So that area, 7.6 times 10 to the negative 24th, that's 0.0 and then 21 more zeros, 7.6. So if I make it a percentage, it's 21 zeros and then a 7.6%. Woof, the odds of that happening are not great, Mr. Kulik. So since that probability is so small, it's essentially impossible that our randomly selected sample could have been that bad, had a mean that bad. What that's telling me is then that the installation time of these two graphic cards is meaningfully different. The new card is meaningfully slower than the old card because the mean that I got on my new installation, the odds of that just being like, oh, it was really the same installation time as the old card, I just drew a crummy slow sample, is so astronomically small to say that it's basically impossible that that could have happened. So what I can say is that the two things are meaningfully different. How about many of us are in like AP or HL science class, currently or past? I think you'll probably have to do this at some point in a lab to do this same calculation here. Does this sound very much like what we do in a science setting? Or probably even in psychology, right? Like if you're doing some psychological study, you're often looking at, is this group meaningfully different than this group in terms of how they see something or the way they behave, right? If you're looking at, are two things different, this is basically what we're talking about, right? You want to measure that mathematically. Like, are they different? All right. So in summary here, it means that since it's highly unlikely that our randomly the sample we randomly selected could have been that bad, we should be confident that this sample of new cards is very likely to have a higher mean installation time than the old graphic card. So that's the summary of kind of what we just did. Now we're going to formalize this a little bit as we go, but this is just like giving you an example of a situation and like testing if two things are different, right? You guys feel like we understand conceptually what we're trying to do here? Yeah, there's something you did one way and you had something you did another way. The old way, you have all this data on how long it takes on average, standard deviation for that. And you have this new way that you think is going to be slower, faster, better, worse, or something. And you go and you try it, and you're like, okay, this is the new mean I got based on this. Is it possible that this is really the same as the old one, right? Or was this meaningfully different? And that's basically what we're testing. All right. The other situation that we're going to be looking at is if I want to look at are two variables related to one another, right? So like, is this one thing causing another thing to happen, or at least associated with another thing happening, right? You're thinking about cause and effect relationship. Again, does this sound like what you want to do in a science setting or social science setting? Like, does taking this medicine cause a reduction in measurable virus load? Does, doing this treatment cause or result in a measurable reduction in symptom? Like this is exactly the kind of thing you'd be doing in medicine or in a psychology setting. Is this treatment cause a meaningful improvement in some patient measurable outcome? So what you do is you start with what's called a null hypothesis. The null hypothesis we abbreviate with the symbol H with a subscript 0. The way you read that symbol aloud is it's H naught. The null hypothesis is basically a statement of what you're trying to prove. So that is, we start by assuming that our hypothesis is going to be true, that the two variables are related to one another. And our experiment, our data that we collect, is either going to support or reject that hypothesis that the two things have some relationship. So, or have no relationship. So the first one, the null hypothesis would have been the time is, or the average install time for the new graphic card is 2 minutes. That it was the same as the old install. The other, if you have a null hypothesis that that the two things are the same, the opposite of that, or the alternative, we call the alternative hypothesis, and we'll abbreviate that either H with a subscript number 1 or H with a letter A for alternative. This is the opposite of what you're trying to prove. So you can't prove a negative, but you can say that you reject the negative, and you can say you can support. You found evidence in support of this. So your experiment, that's what we just said. So for our last example of install or graphic card installs, the alternative hypothesis would be the mean time for the installation is greater than 2 minutes. That's what we were trying to prove, right? What we thought was going to happen. And now, in this case, note that this is not the exact opposite of the null hypothesis. What would be the exact opposite of mu is equal to 2? Mu is not equal to 2 would be the exact opposite, right? What part of the not equal to 2 am I missing with greater than 2? Less than 2, right? That would be the other half of not equal to 2. Means it would be bigger than 2, or it could be less than 2. Everybody's okay? And when we dive into this a little deeper, we'll show how to handle that numerically. So the way that we're going to test if these two things are really different, we're going to be using what's called a t-test. The t is talking about a t-distribution. We haven't talked about probability distributions in a lot of detail at this point, so you don't, conceptually that's going to be kind of a gray area. But just think about like how we build like a histogram. right? We built histograms last chapter, where it's like range of values and a frequency, right? We think about that x-axis being a continuous axis, and instead of using frequencies, we're using relative frequencies. What's the difference between a frequency and relative frequency? Yeah, relative frequency is a percentage. Exactly right. So like the area under the relative frequency graph is going to add up to 1, because all your percentages need to add up to 100, right? So it's basically a probability curve now. But that's kind of what we'll be using. So let's look at a specific example and kind of start talking through null and alternative hypotheses. Start setting this up. So it says here, a factory produces light bulbs that are known to last for 8,000 hours on average. That's historically what is true, right? That's the old mean. A new type of light bulb has been developed by engineers, and they claim it should last for more than 8,000 hours. That would be like my new mean should be greater than 8,000. The management is concerned that the cost of the process of producing the new type is more expensive than the traditional method. So if the average lifespan of the light bulb isn't significantly more, it's probably not worth building this new light bulb, actually producing it, right? So we engineered it. Looks like it's going to be more expensive to make. The engineers say it's a better light bulb, but like, we need to test this and make sure it's actually better or different even than the light bulbs we're producing, because it's going to cost more money to do it, and we're not going to bother doing it if it's actually an inferior product or the same product, right? And in fact, there's probably some threshold of better at which it starts to make sense for us to actually build this thing rather than just keep making the old one. So let's continue on. Okay, and so management decides they can justify shifting to building this new light bulb if they have evidence that the new light bulbs do have a longer lifespan than the 8,000 hours that the old ones are averaging. So to test this, they took a random sample of 25 of these new light bulbs and found that they had an average lifespan of 8,600 hours, and the standard deviation of those new light bulbs was 1,000 hours. Is everybody okay with what's happening? We have these old light bulbs and new light bulbs. We want to test that the new ones really last any longer. So we took a random sample of the new light bulbs. We calculated a mean lifespan and a standard deviation. And what we want to do is make some kind of analysis here to figure out, are they really any different? So our question is, do we have enough evidence to justify switching to making these new light bulbs, right? So let's walk through this again. So again, this is just a summary here. So what we're essentially asking is, what is the likelihood for the random sample of 25 light bulbs that has a mean of 8,600 hours to have been picked, even though the actual lifespan of those bulbs, the average of the total population really is still 8,000, right? Was the possibility that we picked 25 of these new light bulbs from a population that still had an average lifespan of 8,000 hours, and we just got an unrepresentative sample that looks like they last longer when they really don't. Does everybody feel okay with what I'm getting at here? So let's start by setting some stuff up. The mean of the old light bulbs is 8,000 hours. The mean for the new light bulbs is 8,600 hours. The standard deviation from the new light bulbs was 1,000 hours. And now we need to start by writing our hypotheses. So we need to write a mean, or a null hypothesis, and an alternative hypothesis. Everybody good? So our null is that the new light bulbs are really the same as the old light bulbs. That is that new mean is really just 8,000 hours. The alternative is that, what is it that we want to try to show? That they last longer, so specifically we'll say that greater than 8,000 hours, right? Because we want to show that it lasts longer. Now depending on how, yes?
Sorry, but you can finish that.
Okay. Depending on how things are actually formatted in the question, sometimes that, like the alternative is like the question that you're being asked, and sometimes it's going to be the null. Just kind of depends on how the question is formatted.
Even though it's like more than 8,000 now, it doesn't like prove that it's like 8,600. So like how does that work?
We'll get to it.
Okay.
Yep. We'll get to it in a minute. So we're just kind of walking through slowly, like translating, because this is not easy or not natural way of thinking about this. This is actually pretty high level idea. So I'm trying not to rush our way through it. Now to test this, we need to look at our sample, right? So our sample that we took says that we need to do, or we got 25 light bulbs. The average lifespan of those light bulbs is 8,600 hours and at a standard deviation of 1,000 hours. So the tool that we're going to use for this is called a one sample t-test. Notice we're sampling one thing, right? Just the new light bulbs. You're not going to be required to do this by hand on an IB exam. All you're going to have to be able to do is get into your calculator and interpret the result that comes out. So my standard for you is the same. Everybody good?
So for the test, we'll just have to know if we're going to accept it or reject.
You'll have to be able to get the data into your calculator, just output the number and decide what that number means as far as accept or reject.
Okay.
But you will not have to show the workings for how to do this by hand. Okay, so everybody's on the same page? So, you want to start by pressing the stat button on your calculator. And needless to say, at this point, when you see the calculator screen pop up, what am I going to say? I invite you to take out your calculator and follow along if you'd like. I have a set of 5 calculators here on my desk. If you don't have yours, if you'd like to borrow one to follow along with, if you get to the homework and you're like, man, how did we do this again? And you can't remember the calculator commands, what should you do? Go back and find the lesson and watch it. There's 2 of them plugged in to the power strip there. You can grab a calculator to borrow while yours is charging. So again, what I've done here is I've pressed the stat button on my calculator. It's the same place we've gone to type data into our calculator. I'm going to go over to the Tests tab. So notice we have 3 tabs, Edit, Calc, and Test. We're going to go over to the Tests tab. The command that we want is the t-test. That's command 2 on my screen. The one sample t-test on your calculator is just called t-test. Everybody following along, still with me? Okay. So select that t-test. When you do that, it's going to open up a window So you have two options. It's going to ask you what kind of input you have for the calculator. Do you have data or do you have statistics to input? In this problem, we have old mean, new standard deviation. Those are statistics rather than raw data. So we're going to choose the stats option. So we have the mean for the null hypothesis, which is the 8,000. That's the first input, the old mean. The second input, the x bar, is your new mean. That's the 8,600. Remember, we sampled 25 light bulbs and found the new mean of 8,600. Sx is the sample standard deviation. That is the standard deviation from the 25 light bulbs. That was 1,000. N is the size of our sample. There were 25 light bulbs we looked at, so that's 25. And then down here, where it says mu, and then we have three options, is going to be based on your alternative hypothesis, right? Our alternative hypothesis is that the new mean was greater than the old mean. So I'm going to pick option 3, where I have mu greater than mu naught. Remember, mu naught we should read as old mean. Does everybody feel okay with how I filled the numbers in here and selected the options? Once you've done that, go ahead and scroll down to where it says calculate and press enter. So this is the output from your calculator. If you're following along, did you get the same output that I have? Sam and Quinn shake their head yes, that's great. So how do I use this information? Oh, that's if you had picked draw, that's what it would have shown you. Notice the p-value here, that's your probability. So the draw, you can't tell, but this little piece over here is shaded in. That's why it's a little bit thicker, darker blue than the other part of the curve. If you look at the left end, it's not quite as thick and dark as the right end because it's shaded over there. So to interpret this, that the t was 3 and the p was 0.00310 or thereabouts, rounded to 3 sig figs. You can go if you need to. So we'll talk about what to do with these things. I mean, I can do it if you want. Yeah, you won't walk and save those steps, you know? Yes, sir.
So I'm a little bit confused. What information are we putting in and what information are we giving out? Are we putting in the original mean? Are we getting like a mean out?
This was the data we typed in.
Yeah.
This is what popped out.
Okay.
Okay. So this was the old mean, the new standard deviation, the sample size, how we wrote our alternative hypothesis, and then we hit calculate. Yes. Okay. And what spit out is these outputs. And we'll talk about how to interpret that in a moment. Okay, what that means and how to summarize what does this tell me about the experiment that I did. Did it support that these light bulbs are different, or are they really kind of the same light bulbs?
Where do you see that we round the
3 sig figs, like everywhere else in the class. So 0.00310, right? Beginning zeros not significant. Trailing zeros are if they're after a decimal point. Okay. So the two numbers that we care about to analyze was there, to answer the question that the corporate office asked us, like, hey, are really these light bulbs any better than the ones we're already making for pretty cheap? We need to look at the t-value and the p-value. The t is what's referred to as a critical number. And basically it tells us how far away from the mean our distribution is from the original mean. The old, so how far away is the new mean from the old mean? So what this is saying is that in our problem, the old mean was 8,000, the new mean was 8,600, that essentially that 8,600 is like 3 steps away. So if you look at the x-axis, there's 1, 2, 3 tick marks. That's basically where the 8,600 is. Is everybody okay with that idea? Really, you know, like this number is important, but by itself doesn't give us a whole lot. In the previous era, what you would have done is you would have taken that number and used it to generate the p-value using a table or something. That's how Mr. Kulik had to do it before the advent of like these modern programmable calculators. Old guys. You had to like look this stuff off a table basically, which was not a lot of fun. The number that we really are interested though is the p-value. That p stands for probability. So what it means is that there's essentially a 0.310% chance that the population, if the population light bulbs we sampled had a mean of 8,000, that we could have selected 25 light bulbs that would have had an average of 8,600. So 0.3% chance that if the light bulbs really, the new light bulbs were really the same as the old ones, that we could have pulled 25 light bulbs and gotten that average. Not very likely, right? What is that saying to us then? No, it's that the new light bulbs are different than the old ones. Because the chances of us pulling 25 old light bulbs and getting that 8,600 average is 0.3%.
Oh, so it's more likely that.
It's more likely that these are meaningfully different light bulbs than the old ones. Is that, you see what we're saying there?
Yeah.
So it's almost impossible that we could have taken old light bulbs and drawn 25 of them, gotten that average. So what does it all mean? Starting with the assumption that the light bulbs had a mean lifespan of 8,000 hours, basically 0% chance we could have randomly selected the 25 light bulb sample that gave us the new mean of 8,600. We should say then the null hypothesis is rejected. The null hypothesis is that the new mean is really the same as the old mean, that the light bulbs, the two different types of light bulbs, are really kind of the same. The new light bulb wasn't any better than the old light bulb. We'll reject that and accept the alternative hypothesis is that the new light bulbs really are better than the old light bulbs, that they do actually last longer. Now, how long they should last, we did not determine. We just found like a preponderance of evidence that says, no, these new ones are better. How much better? I can't tell you that. More analysis is necessary, but they are better. Now, what we did up there was called like an upper tail test. Because if we go back and we look at this picture, we're looking at like the upper tail of our distribution, right? The right-hand side of it. Is everybody okay with that? Now, depending on how you write your hypothesis, oops, I'm going the wrong way. You can have upper tail, you can have lower tail, and you can have two-tailed. Okay? Let's look at another example. Basically the same setup. But this time our sample was 8,200 hours was the average on our sample. We did the same thing, still 25 light bulbs. We still had old light bulbs with an average lifespan of 8,000. Still the sample Standard deviation was 1,000 hours. Everything is the same except the new mean was only 8,200 instead of 8,600. We're going to check the same thing. Is it possible that I was just pulling from light bulbs with 8,000 hour average and I got 25 of them that average out to 8,200? How possible is that? So we're just checking again. So we do the same setup. Look at what happened this time. So we did the same thing on our calculator. Look at the p-value this time. Look at the distribution of where we shaded.
It's a lot.
It's a lot more distribution, right? That p-value is quite high. So that p-value is 0.164, rounded to 3 sig figs. Basically, it's saying there's a 16% chance that this new set of light bulbs is the same as the old set of light bulbs. I could have drawn 25 new light bulbs from when we really had the same 8,000 hour average and gotten a sample that had 8,200. Depending on what you're doing, that may or may not be enough evidence to say, okay, these two things are the same. So we'll talk about the standard, how sure you need to be, how good does that probability have to be that the two things are different before we can actually say they're different. But that was a lot better chance that those two sets of light bulbs were really the same set of light bulbs, right? That there wasn't a meaningful difference. Going from 0.3% to 16.4% chance that they're really just the same light bulbs. It's a big jump, right? What changed was the average from our sample. Cool.
If it was like this one, it tells us like you want to see the difference between like the old light bulbs and the new light bulbs, so we knew that we had to be like that. But how do we know like it was supposed to be like the button above the light bulb? Like how do we know?
Oh, here?
Yeah.
Because we're still testing to see if the new light bulbs were better.
Okay.
Right? If the new mean is better than the old mean.
Okay.
That's still what we're looking for, right?
Okay.
Because we're not going to build a more expensive light bulb that works worse than the old one, unless we're like really kind of unscrupulous business people,
Okay.
right? Like, we'll just make you a crappier product and lie to you and say it's better. So you have to buy more of them, that you have to replace more, profit goes up, right? New and improved in terms of me making more money, not you getting a better product. But does that make sense? Okay. So we're going to look at a different example now, where we're going to do a lower tail test. Here we want to look at, actually, are the new light bulbs worse than the old light bulbs, right? What if we built this new light bulb and it's like, ooh, boy, we use some inferior products and it's actually worse than the original. So let's say everything is the same, but this time we think that the new light bulbs are actually worse than the old light bulbs. This is going to be called a lower tail test, because this time we're checking if the new mean is less than the old mean. Okay, so the previous ones were upper tails. Now we're doing a lower tails. You guys see what we're saying? Okay. So all the numbers are the same. The only thing that changed was the alternative hypothesis is now a less than 8,000 instead of greater than 8,000, right? But all the means and standard deviations, all those numbers stayed exactly the same. So we'll take that, go to our calculator, stat, test, t-test, run through. Oh, great googly moogly, look at what happened here. Look at that probability, 0.836. Basically an 84% chance that I could have pulled from a sample of light bulbs with means of 8,000 and got, or something worse than 8,000 and still gotten an 8,200 mean. So pretty likely that this new mean is actually worse than the old, right? 84% chance I could have pulled, you know, okay. All right. The third way you can kind of formulate this is as a two-tail. The two-tail is if they're straight, not equal, where it could be better or it could be worse. Right? So same idea, the same sample, 25 light bulbs, mean 8,200, standard deviation 1,000. But this time I just want to know, are this new light bulb different in any way than the old light bulbs? Are they better, are they worse? I don't know. Are they different? So again, everything the same except for the alternative, which is now not equal to. Everybody good? So set it up the same way, except in my t-test, I pick the not equal to option. That's the two-tailed because we're looking at either side of the mean. So we're looking at both are things better or are things worse. We look at that, we got, you know, basically 32.7% there. Yes?
So if the shade region is on just on the right side, and if it's like, it's just on the right side, it means that there's a low, there's not much of a difference.
So if the shaded area is on the right, it means you're testing is it the new mean better than the old.
Okay.
That's all it's saying. It's how much of it is shaded is telling you how likely it is that you could have gotten that you could have been drawing from the same sample or something with the same mean and gotten that particular sample. So if we have a 32.7% chance, that means like 32.7% of the time I could have been sampling from a mean of 8,000 and gotten something that was 8,200. So that's pretty likely that that could have happened, right? Fairly good odds that I could have gotten that. Okay. So the question here we've been kind of dancing around is like, if I look at that p-value, how good is good enough for a p-value to say like, yeah, these two things are different, you know, like give me the alternative rather than the null, in which case, you know, which is just basically saying the two things are really the same, right? So let's kind of run through that here. So these are the four scenarios we ran through, right? We did greater than 8,000 where the new mean is 8,600, greater than 8,000 where the new mean is 8,200, less than 8,000 where the new mean is 8,200, and not equal to 8,000 when the new mean is 8,200. Everybody's okay? So these are the four situations. So to summarize here, the first mean, or the first probability was 0.00310% that the null hypothesis was correct. That's awful small, right? Very likely it's incorrect that the new light bulbs would have been better. The second situation where we had, or the third situation where we had the probability of 83.6% that the null hypothesis was correct. That's awful good, right? What about the two in the middle, the 16% and the 32.7%? Like, pretty clear that like almost zero, pretty sure what to do with that. Almost 100, pretty sure what to do with that. What about these values in the middle? Like, are either of those like good enough to say anything? So what we typically do is we're going to have an industry standard called like a level of significance that we're gonna compare our probabilities to. So depending on the industry and how sensitive or how important it is that you are right, that the two things are different, that level of significance can be higher or lower. If you're dealing in like a medical, like a medical field, that level of significance is going to need to be quite low. You really have to know that like this is meaningfully different than doing nothing, because almost all treatments have side effects, and you don't want to deal with side effects if really you're doing it nothing at all, right? Or potentially like the side effects kill you, right? All medicine is actually poison, it's just the dosage that matters, right? Too much of anything kills you, even water, right? Drink enough water, you disrupt your electrolyte balance, and you die of a heart attack, because you can't, the muscles in your heart can't work. Anyways, we use a level of significance. So that would be stated for you in the problem. It'll tell you in the problem what the level of significance needs that you need to compare to. Typically, 5%, 10%, 15%. It usually is kind of maybe a 3% if you're in a strict situation. Occasionally it's 1, but your most comments are probably like 1, 3, 5, 10. It'll just stay in the problem, the percent. The letter we used to abbreviate this level of significance is the Greek letter alpha. So that's that little symbol there. Looks like the Jesus fish. If you're drawing it on your sheet of paper. We're a Catholic school, so everybody probably knows what I mean by that. So it's basically just the threshold for when we're going to say, okay, that probability, that this could have been nothing different, I could have just been drawing from the same stuff. If that probability is below the level of significance, then we're going to agree that, yeah, the new thing is different than the old thing, that it's better or worse or just different, whatever our alternative said. So again, the most common levels of significance, 1, 5, 10, 3, 15, whatever. So our p-value, that's what comes out of the calculator. All we're going to do is compare our p-value and our level of significance, and then that'll tell us whether we should be accepting or rejecting our null hypothesis. So we say when p is small, there's a very small chance that you could have gotten a worse sample than the one you currently have, making it a very bad sample, meaning that you got really unlucky. Or, alternatively, that the stuff you're pulling for is actually different than you thought, right? That it's meaningfully different in some way, either it's better or worse or just different. If the p is big, there's a very good chance that what you're pulling from was really the same as the old thing, meaning that they're just kind of the same. That you have a very representative sample if you're drawing from the original stuff. So, the rule, if p is greater than or equal to alpha, note that it's a greater than or equal to, we would say that our data supports the null hypothesis, so we accept H naught, and by accepting H naught, that means we in turn reject the alternative, i.e. H1. That's the language we want to use. We accept the null, we find evidence in support of the null, evidence in opposition to the alternative, we accept the null, we reject the alternative. Everybody okay there? I will be picky about verbiage here, okay? If you have that p is less than alpha, again, note that it's a strict inequality in this direction. you would say that your evidence contradicts the null hypothesis, so we should reject H naught. And by rejecting H naught, in turn, we find evidence in support of the alternative. So we accept the alternative, i.e. accept H1. Do you need to memorize when you accept and reject? 1000% yes. 1000% yes. You absolutely need to have that. So again, in summary, this is where we're at. Yes, Nicole?
If you say that contradicts, like obviously like except for the best ones, but like if you said contradicts, it would be wrong.
If you said the evidence contradicts
Yeah.
this, that would be okay.
Okay.
So you will then reject
Yeah.
da-da-da.
Okay.
So like, it's just about making sure that you're phrasing it. Like evidence can't accept or reject. You do that,
Yeah.
right? Evidence is either for, in support of, or contradiction of. You know what I mean?
Mm-hmm.
So it's like an English language thing.
Okay.
Like making sure you're being clear about what you mean. So as a piece of verbiage here, fine to say reject hypotheses, right? Not technically correct to say accept, right? What's a hypothesis? It's just a guess, right? You don't actually say your guess is right in science. We can't prove that. What do? We just prove that it's not wrong. And as long as it's not wrong, we're going to go with it until we find evidence otherwise, right? So instead of saying accept, you can say fail to reject. Is a better way of phrasing that. Now, while we're talking in class, you can say accept.
But on the test.
On the test, I would like you to write fails to reject. Because it is more precise, and it is actually what we're doing in a scientific setting, right? We don't actually accept hypotheses. You can't do that. You can just fail to reject it. Be like, oh, looks like it still holds in this situation. Your famous example is gravity, right? Like Newton comes up with the laws of gravity in the late 1600s, early 1700s. Wasn't until you started getting electricity and stuff till you started seeing oh, the planets aren't moving exactly like we thought they should. And now it's oh, it works. So Newtonian physics works really well until things get really, really big or really, really small. So everyday stuff worked fine until you had telescopes big enough to really, or microscopes good enough to. What replaced Newtonian physics? It was Einsteinian. So E equals mc squared is the refinement. Or special relativity, I think. Is it special or I can't remember which one is which. But the one where basically space is gravity is just curvature of space is the idea. All right, so what can go wrong here? So a p-value, unless in a non-theoretical setting, isn't exactly 100% or 0%, right? There's still some possibility that ooh, boy, we just got the unluckiest of the unluckies. Couldn't I just gotten a lottery ticket instead of getting this terrible sample? But hey, I did it. I got that terrible sample that was really from the same thing. It was just got lottery ticket odds hit. So when that happens, when we make a mistake, it's either a type 1 or type 2 error. So when the truth is that the null hypothesis is true, but we rejected it, that's an error. Or in the situation where the alternative hypothesis is true, but we did not reject the null, that's an error, right? So when the null is true and we didn't reject it, we did the right thing. When the alternative is true and we reject the null, we did the right thing. The other two situations, those are mistakes, right? There's some kind of an error we made. So when we reject what was true, that's a type 1 error. So this is if you're taking a COVID test and you don't actually have COVID, but it says that you do, this is a type 1 error. The null hypothesis in the COVID test is that you are fine. The test said you are sick. That's a type 1 error. A type 2 error is when the alternative is true, but it says it is false. This is when you take a COVID test and it says you're not sick and you really are. So it helps in the medical test example, something we probably all have firsthand experience with. Now, in a medical test setting, which one would you rather have? Type 1 errors or type 2 errors? Type 1, right? You'd rather tell people that aren't sick that they're sick. Why? We can give them a second test, just to make sure. Because the odds of you getting the wrong outcome twice is like an order of magnitude worse. The probability goes down astronomically. You know, like if I have a 1% chance of getting it wrong, and then get it wrong 2 times in a row, that's a 1 in 100 chance of that happening. You know, like, it's multiplicative. So like, you know, if you are into like Olympic sports, they do the drug testing for the Olympic sports. They always split the urine sample into 2 batches, like an A and a B sample. Any positive test, they run it again in case of a false positive, right? Yes. Does that make sense, guys?
Yeah.
And what we're talking about here? Okay. All right. Now, there's a second type of t-test. That's a 2-sample t-test. Now, I have pooled here in parentheses. We'll talk about what that means in a moment. So let's look at the situation. So there's a new situation, right? The comparison of the amount of nicotine that could be inhaled from cigarettes of the same brand was found to differ between countries. There is some suspicion that local cigarette companies boosted their cigarettes' nicotine content to maintain or increase present addiction levels. A study of 40 randomly chosen cigarettes was conducted to investigate this issue between 2 European countries. The recorded average level of nicotine content in cigarettes in both countries is given below. So, what's the difference in situation between this and the previous one? In the previous one, you had an old standard. You had like, this is the known mean, right? Do we have a known mean here? No, right? We're taking 2 things and saying like, are these 2 things different? But we're not comparing one against the other, right? We don't have a standard. We just had like, oh, this is, you know, like, are boys smarter than girls? Right? Like, we don't know how smart boys are or girls are, but we can compare them against each other. Are boys born after 2000 smarter than the boys born before 2000? There we're comparing it against an old standard because ideally we have testing scores from boys before 2000 that are historic that we could compare the mean against, right? You could find that from the entire population and have like a real average, as opposed to like current boys, where it's like, well, we don't know, we don't have their end results, because they're still growing and like learning things. Do you guys get the difference between a 1 sample and a 2 sample? Okay, so let's look at the numbers that we sampled. So country A, we had a mean of 0.85 milligrams nicotine per cigarette with a standard deviation of 0.2 milligram per cigarette. And in country B, we had a mean of 1.3 milligrams per cigarette with a standard deviation of 0.18 milligram per cigarette. And we want to ask, is the nicotine content there different between the two countries? And want to test that against the 5% level of significance. Well, how do you know? What's the probability that they are different? That's what we're going to find out. So, again, as I mentioned, this is a fundamentally different kind of test because here we're comparing two unknown things to see if they're different, as opposed to comparing one thing against a known, like, reference. Everybody's okay? That's why this one is a 2 sample, because we're sampling from 2 things, as opposed to the previous one we're sampling from 1 pool. Just like before, not expected to be able to do this by hand. You just have to be able to get into your calculator, get the result out, and interpret the result. It's a black box for us as far as this goes. DeGrande, when you did AP Stats, did you have to do this by hand, or was it just still input in your calculator and interpret?
We had to do it like half and half, but there's some times we have to.
Okay, so there was some expectation we were able to demonstrate this by hand?
Yeah.
We do not ask you to do that.
Yeah, I know. I was happy when you said it for the 1 sample. I was
Yeah.
pretty happy to hear that I don't have to write everything out.
Yeah. I will ask you to do it for chi-squared,
Okay.
but that's as much simpler than this
Yeah,
is.
right, yeah.
Okay, so we start the same way. We write out our 2 hypotheses. So the null is that the nicotine contents are the same. Or symbolically, we'd write just mu A is equal to mu B. Everybody okay with that? The alternative is that they are different. Or that mu A is not equal to mu B. Note that there's 2 different ways to write are equal or not equal to, right? Everybody can see all we did was subtract mu B from both sides in either situation. Okay. So to do this, into our calculator we go. We press the stats button. We go over to the test tab. This time we pick the 2 sample T test. Note there's also a Z test there also. We don't do Z tests in this class. Lucas is like, good. I did that. Don't need to do it again. This time we pick, just like before, we have a data option and a stats option. We're going to pick the stats option. We're going to input the numbers. So for x1, that's the first mean. That's 0.85. SX1, that's the sample standard deviation from the first country. So that's 0.2. N1 is the number of things in our sample that was given to us as 40, remember? If we go all the way back here to the problem. Study of 40 randomly chosen cigarettes. So that's why it was 40. And then the mean and standard deviation from the second country. And our alternative hypothesis is that the 2 means were not equal. That they were given different cigarettes to different countries as far as the nicotine content goes. And let's compute. Oh, yeah, hold on for one more moment. For our t-test in this class, we're always going to choose the pooled option. The pooled is always yes in this class. Pooled just means that the 2 samples have like equal variance. Never going to do non-pooled. Lucas, did you guys do that in AP stat? Do you remember?
I honestly don't.
That's okay. Just remember for this class, everything is pool.
It's cool, okay.
Yeah, bring your bathing suit. It's a pool party here every day. All right, so you type that through and it spits out. What do you notice?
No.
Well, look at the probability.
0.
Twice.
9.
Yeah, 9.93 times 10 to the negative 17th. Ay caramba.
Oh, I'm gonna.
So how likely would it have been that these two things were the same? Basically 0, right? These were definitely different. Almost definitely, right? Notice when we did our two-tailed, can you even see where they shaded on the two tails? I mean, I can't. It looks like just the graph, right? It doesn't look like there's any shading at all. But that's as expected because it's basically 0. So these things are definitely different, right? The probability of them picking them that they were the same is like basically 0.
What number is alpha?
5%. We went skyrocketing under that, right? It would have almost not even mattered. We were so close to 0. I guess it would be submarining under it because it's under. It won't be going skyrockets. Submarines. Let's just stop here for today. I mean, I don't want to get into like another example. I feel like my voice is getting a little scratchy here. I've been like womping for a while. We're on slide 29 of 44.
I have to buy Oreos.
What?